So as we just mentioned, it is very important that how you choose your step size, because if you choose it too big, you're going to have a condition like this. And as you can see, it's going to have overshoot, undershoot, and we are not going to consider actually the thing that we want. And it is very important to choose something that not only can be some kind of stable, but also can be accurate. So since we are talking about step size, we do have two rules for that. The very first one is about stability. If you would like our system to be stable but not 100% accurate, we do have the first one. The first one which says that your step size should be smaller than 2 divided by lambda max. If you guys remember, when we had a system, we had to find something we called as eigenvalues or lambda. So based on that specific lambda, obviously, maybe we have more than one, we have two or maybe three, we have to choose the maximum one, and based on that, we can find the step size. But if you would like your system to be accurate, there's another rule that would say that h should be smaller or bigger, should be smaller or equal to t fastest, which is obviously the time constant, divided by 10. If I would like to give you an example, imagine that you do have the system that it has two poles. The very first pole is -2 and the second one is -50. If you would like to have your system to be some kind of stable, the very first thing that you have to do would be 2 divided by 50 itself. So if you have that one, your step size is going to be 0.04 seconds. But if you would like to have your h or some kind of choosing the step size to your system be accurate like this, you have to choose what? You have to choose the t fastest, which is the time constant. You guys know better than me how to find it, divided by 10. And after that, you can make sure that your system is going to be accurate. So let's talk about the stiff system paradox, because at some point, maybe you would say that, okay, let's try to find the best one. The best one means that has the highest accuracy. But at some points, you would see that your simulation works fine, but when you're trying to work it in an actual world or actual system, your controlling has to do lots and lots of computation, while you don't need all of that. Imagine that I do have this system that I found out this fast transient time, or tau, is going to be something like this. So this one supports explicit methods, I mean like Euler, and RK4 actually was a method that I somehow got rid of that, but you can search through the internet, is another method like the Euler in order to linearize your system. It's good to know that. So at this point, this factor or this some kind of analogy forces us to choose h as something 0.002. So simulation, it means that for a 10-second slow wave requires 5,000 wasted calculations just to satisfy stability for what? For the transit that you don't care about. But what is the solution? The solution is something that we call as impact method, something like backward Euler. You can just kind of read about it. I don't want to. This is something that I would like to just bring up. It's mostly like FYI. So at this point, we are going to calculate the future state based on what future conditions. So this guy is going to allowing the algorithm to step right as to skate right over the fast transient. It means that instead of just choosing our h, something so small that is going to consume so much time and waste our energy, we can use other kind of methods that they can use the future prediction while they're using some kind of the bigger step size. And instead of just having, for example, 5,000 of steps, we only have what? We only have, maybe we need some kind of 10 total steps, and it means it saves a lot of time for us. So let's talk about the real world, because so far we were talking about the simulation, we were talking about some kind of what is the best way, what is the accurate way, but we still have some constraint. As I just told you, we cannot just do everything that we need during the mathematical, during some kind of the designing phase, the simulation phase, and say that, okay, that's good, let's build it. We do have some constraint, and the very first constraint that you're going to face is about saturation, because believe it or not, when you're dealing with the physical system, those physical systems have some kind of saturation mode. It means that, for instance, in your simulation part, you assume that your system can handle till 15 volt. But as soon as your system or your physical system reaches out to 10 volt, it means that it's just saturated. And this guy is just saturated over here. Not only cannot follow up the increasing phase, but also the decreasing phase is going to cause some issue. Another thing would be about the time delay. Obviously, because of all of those connections, because of all of those some kind of the time delay that would happen between the feedback loop, between the some kind of that signal, the command signal that you give it to the system, you would have this small amount of time delay, and this time delay could ruin everything. Another thing that most of the time we don't consider is about the noise, because we assume that in our simulation system everything is ideal. We don't have that problem. Our sensors are working completely fine, but in the real world we do have the noise. So that noise is going to cause us some issue. And finally is about the quantization. It means that digital sensors could cause limit cycles and jitter. It means that we can have the step size that we want, but in the meantime our sensors cannot handle that. So while trying to deal with that, you have to be very careful. Another thing that I would like to bring up is a fact that is some kind of terminology that we call it as a wind up focus. That would happen in the PID controller. So what is the idea? Imagine that you do have the motor, and as we just know, that guy is going to saturate at 10 volts. But the linear PID mathematically demands 15 volts. This is the issue happen. And the internal integrators wind up. It means that at this point, instead of just reaching to the 15, your system actually reaches to 10, while the system is trying to push so hard to reach to the 15. At this point, your error is going to wind up, your error is going to accumulate, and when you're dealing with the I controller, part of the PID controllers, it means that it's integrator. It means that that guy is going to accumulate all of the errors that he had, and it's just like working as a dam. It means that all of the water is going to store behind the dam, and as soon as your some kind of error finally reverse, it means that you reach to the point that actually your system can work. Imagine less than 10 volt, all of those errors are going to inject inside your system and is going to make catastrophic issue. So if I would like to somehow summarize everything that we learned so far about the methods, about what are the best for accuracy and so far, the very first method that we learned was about Laplace method. So that was the best for a system inside. We would like to have some kind of an idea what is happening in the system. The accuracy is so good, and some kind of the speed and cost is not that much, and it cannot handle the nonlinearity, and that was one of the main red flags. Another system that we learned was about the state space. It means that at that point we have multiple input and multiple outputs, and we do have the internal dynamics. Again, it's going to be exact, but at some point is going to cost a lot, because as you all know, if your A or the DNA of the system is going to be high, it means that your n times n, or your rows and columns, are going to be too many, like 10 or 20. You do have to deal with all of those confusing and some kind of complex matrices, and finding the right value is going to take so much time. It's not going to handle the linear case. As we just saw, we learned something about the Euler method, or we call it as a forward Euler. It means that this guy is working on the simple simulation. By considering the h, by considering the step size, we can use it. So the accuracy of this guy is something that we call as OH to the power 2. It means that your system is going to deal with the changes, or deal with kind of some kind of the errors as the way that it likes. And instead of just, for instance, if your error reduced by half, this system is not going to say that, okay, I'm going to reduce it by half. I'm going to reduce it by what? By 1/4. That's why we somehow like this system. And the very, very important thing is that this guy can handle a nonlinear case. RK4 is something that, for FYI, you can some kind of later on read about that. But one important thing is that this guy is OH to the power 5. It means that if your error reduced by half, your actual error that your system would handle it would be reduced by 1/2, or half to the power of 5, which is very, very impressive. Obviously, it's going to increase your computational time, but it's going to worth it. And also can handle the nonlinear modes. And then we do have the implicit methods, which we do have the system, though, which is not very important. So the next thing that I would like to have is, again, another some kind of example. This is going to be the final example that we do have related to this part. And the next episode, which is, I'm super duper hyped about it, is going to be the fact that we are going to have multiple systems side by side. Because if you guys remember, one of the reasons that actually we use the Laplace transformation instead of the timing domain is that we can handle multiple systems together. So let's look at this question. The question is simple. The question would says that I do have a system. I do have obviously a mechanical system, and this mechanical system, I do have a formula for that. So that main formula related to the force, related to the mass, and everything, some kind of that could rule your system, would be something like this: mx prime plus bx prime plus kx equals to ft, and ft is going to be your input force itself, and after that you do have the mass and you do have kind of other factors. So imagine that you do have the system that your mass is 2 kilogram. It means that m is 2 kilogram, and your b is going to be 4 newton second per meter, and your k is going to be 20 newton per meter. And imagine that you have a case that your x0, or your input, or the condition at the 0 would be what? Your x of 0 would be 0.1 and 0. So the question asks, write the state space form for this mechanical system. So the very first thing that we have to do, obviously, we have to add all of those numbers, or replace all of those numbers inside this guy, and reach to some kind of an equation for our system itself. And imagine your f of t is going to be 0. So most of the time we just imagine that f of t is 0, and we can find all of the values that we want. So it would be 2x prime to the power of 2, by the way, or 2x second plus 4x prime plus 20x is equals to 0. As you can see, I can do the factor of 2 over here, so it would be x prime, 2x prime plus 10x equals to 0. So this is my equation, and right now I would like to use the method in order to find what? To find the x of t and e to the power of a of t. But the very first thing that I have to do is I have to define two things, because I'm dealing with multiple inputs, x1 and x2. So x1 would be considered as x, we know what x is just about the position, and x2 itself would be the rate of change in position, as something we know as velocity. And also, obviously, x prime, which is going to be what is going to be acceleration. So then, based on that, we can find a couple of things. The very first thing that I can do is what? Is that x1 prime is equals to x2. Obviously, we saw that over here. It means that if the changing in position in the changing position is going to be, if I find the derivative of that, or rate of that, I can find what? I can find the velocity. Another thing that I can find is about the x2 prime, because x2 was already x1 prime, so x2 prime is going to be x1 prime to the power of 2. And if you look at this equation, I can some kind of rearrange everything, and x1 prime is going to be what? Is going to be negative 10x1 subtracted by 2x2. So these two equations, the first one and the second one, is going to give me something that we know it as the A matrix, because if you guys remember, my x prime was ax plus bu. Is that case? So based on that, my x1 prime, x2 prime is going to be what? Is going to be the coefficients of x1 and x2. So if you write it down, you do have 0, negative 10, you have 1, negative 2, x1, x2. So this guy is going to give you what? This guy is going to give you A. By using A and then use the Laplace transformation, I can find what? I can find my E to the power of AT. So e to the power at, use this formula, Laplace inverse. It means that at first I have to find the Laplace of my specific formula that I'm going to tell it to you, and then I have to find the Laplace inverse of that one and put it in the time domain. Laplace inverse of SI subtracted by A inverse. So at this point, I do need a couple of things. The very first one is about what? Is about finding this one and then find the inverse of that. SI means that S times the IGT matrix is going to be what? SS00, and then A itself is just A. So this guy is subtracted by the matrix A that we found, 0, 1, negative 10, negative 2, which is going to give you what? Which is going to give you S, negative 1, 10, S plus 2. As you guys know, in order to find the inverse of this matrix, because it is important to find the Laplace inverse of this matrix, we have to do what? We have to find the determinant, which is going to be what? 1 divided by S times S plus 2 subtracted by 1 or negative 1 times 10 and times. By inverse means that I have to replace the place of S and S plus 2. So it would be S plus 2 and S, and I have to multiply these two numbers by negative 1, negative 10 and 1. So if I do have that, at the end of the day, your final system is going to be what? Your final system is going to be like this. Obviously, it's going to be a little bit complicated, so bear with me. S plus 2 divided by S plus 1 to the power of 2 plus 3 to the power of 2. I have a reason for writing that, because 3 to the power of 2 is just going to be the 9 itself. And I'm going to talk about it, why I wrote it down like this. Instead of just having S times S plus 2 and subtract and plus 10, I wrote it down like this. Then for the second one would be 1 divided by s plus 1 to the power of 2 plus 3 to the power of 2. And for the third value is going to be negative 10 divided by s plus 1 to the power of 2 plus 3 to the power of 2. And finally, I do have s divided by s plus 1 to the power of 2 plus 3 to the power of 2. So at the end of the day, my e of at is going to be something like this. But the issue is that this guy is what is in Laplace form, and I have to convert it back to the time domain. So let's see at something. Let's see at some kind of the review related to Laplace. The rule is like this. Laplace inverse of what? Laplace inverse of s plus a divided by s plus a to the power of 2 plus omega to the power of 2 is going to be what? Is going to be e to the power negative at cosine of omega t, and then Laplace inverse of omega divided by s plus a to the power of 2 plus omega 2 is going to be, again, e to the power negative at, but this time sine of omega t. So as you can see over here, there is a similarity between this guy, and then between this guy and this guy. So somehow I can use them in order to what? In order to convert it back to the thing that I would like. But still, as you can see, it's not some kind of the thing that I would like, because I do have, for instance, my omega is going to be some kind of considered at 3, but my a is 1, and at this point I do have 2. So still I have to improvise. So I'm going to show you how actually that improvise is happening. So for the top left, the very first one, we had s plus 2 divided by s plus 1 to the power 2 plus 3 to the power 2. So in order to make it something like this guy, because somehow I can see the top left is very similar to that, I would say that s plus 2 divided by s plus 1 to the power 2 plus 3 to the power 2 equals to what? S plus 1 divided by s plus 1 to the power of 2 plus 3 to the power of 2. So as you can see over here, my a is going to be 1, I do have it over here, and my omega is going to be 3. Yet, I still do have another one, plus 1 divided by s plus 1 to the power of 2 plus 3 to the power of 2. So as you can see over here, this guy is somehow similar to this one, but instead of just being omega on the top, I do have 1. So what I can do, I can make this guy as 1 divided by 3 times 3 divided by s plus 1 to the power of 2 plus 3 to the power of 2. So at this point, this guy would be exactly like that, but with this difference that I have to put what? I have to put 1 over 3 as the coefficient just beside of that. Obviously, you can find your e to the power of t to top left very, very simple. Let's look at the top right, that we had it as 1 divided by s plus 1 to the power of 2 plus 3 to the power of 2. Obviously, you can see that this guy is so similar to this, so we are going to do the same thing. I mean, I'm not going to do that. You obviously can do it better than me. Let's look at the bottom left. The bottom left, we do have negative 10 divided by s plus 1 to the power of 2 plus 3 to the power of 2. So what would you do? You are going to do the exact same thing that we did on this side. What is that? It means that negative 10 multiplied by 1 over 3 multiplied by what? 1 divided by s plus 1 to the power of 2 plus 3 to the power of 2. Then we do have the same scenario, and the bottom right, which is going to be so similar to the top left, and I believe you can do it better than me by a little bit of some kind of novelty. So that was this final slide of this chapter. As you just saw right now, we talked about some kind of so many different concepts, but the very important thing that I was going to emphasize on that is that your system has some kind of limitation. Not only about that, it means that we cannot use some kind of the method that we knew about some kind of state space, about the Laplace transformation, if we don't have the linear system. If we do have the nonlinear system, means we have to use another method. That very important method was about the Euler method. And then you have to choose the step size, but you have to be careful when you choose the step size. You should be very, very careful about that. We use the 2 thumb rules for that one. To either you need the accuracy or stability of the system. And at the end of the day, we somehow consider the limitation of your physical model. It means means that if everything goes well in the simulation, it doesn't necessarily mean that your some kind of simulation is going to be implemented exactly in your actual system. Your actual system is going to have some limitation, and as you just saw before, we are going to have saturation, the time delay, the noise, and the quantization that you have to be very careful about that one. So I cannot wait for having the next episode related to control. As you can see, it is getting very, very meaningful, and it's also very, very informative, and you, by solving too many questions for some kind of each chapter, you guys are getting better and better. Again, if you couldn't understand any of this part, first of all, try to rewatch it again, and then you can obviously just Google a little bit. But at the end of the day, if you couldn't understand it, you can always ask me. I would be more than happy. My name is Mahmoud Kiasari. Thanks for watching this video. Have a super great day. Not whatever. See you around.